everybody, Miss Sarah here. Welcome to the third part of our review, which we are going to tackle the non-parametric. And without further ado, let's start. So I will show you my screen. So what is non-parametric? It refers to a statistical method in which the data are not assumed to come from prescribed models that are determined by a small number of parameters. Example of such models includes the normal distribution model and the linear regression model. Now, non-parametric has two topics that we have is the chi-square test and the Spearman's rank order correlation coefficient, while the chi-square test has three different subs, and we are going to start with it. So what is a chi-square test? It is an association between categorical variables. So we have, this is our formula, and this is the chi-square test for goodness of fit, and this is the chi-square test for homogeneity, and this is the chi-square test for independence. And we are starting off to the chi-square test for goodness of fit, which is test claims about population proportion. So the test, it claims about the population's proportion. So again, it is a non-parametric test that is performed on a categorical or nominal or ordinal data. So a chi-square test for goodness of fit, this is our example. So in the 2000 US Census, the ages of individuals in a small town were found to be the following. So we have less than 18 is 20%. The 18 to 35 years old are 36%. Greater than 35 are 50%. In 2010, ages of N, so this is our individuals, so 500 individuals were sampled below are the results. So the less than 18 is 121, 18 to 35 is 288, and greater than 35 is 91. Using the alpha 0.05, would you conclude that the population distribution of ages has changed in the last 10 years? So here's our formula. Our graph, our table. So this is the expected one, which is the 20% a while ago, then the 30%, then the 50%. Our observed data is 121, 288, and 91. Then we're going to get our expected data. So it will be 500 because this is the participants times the 20%, and it will equals to 100. Then again, 500 because of the participants multiplied to the percentage, which is 30%, and it will be 150. And we have 500 for the participants. It will be multiplied by 50%, and we will have 250. So chi-square test for goodness of fit. So this is now our new table or new data. We have our observed is 121, next is 288 and 91. Our expected data is 100, 150, and 250. So first, what we're going to do is to define the null hypothesis and the alternative hypothesis. So our null hypothesis, the data meet the expected distribution. Our alternative hypothesis, the data do not meet the expected distribution. Here. So in step 2, we are going to identify our alpha, or the level of the significance, which is the default one, 0.05. And the step 3, we are going to calculate the degrees of freedom here. So this is column minus 1. So we have 2. We have 3 column. And we should minus it 1, and we're going to have 2. We're going to use that in our chi-square test table, and our degrees of freedom is 2, and our alpha is 0.05. So our data will be 5.99147. So now we are going to state the decision rule for our step 4. So the rule will be, if it is more than 5.99, then we will reject the null hypothesis. And if it is less than 5.99, then we are going to support our null hypothesis. Now let's start to calculate the test statistics. So this is our formula. So x squared will be for the chi-square test, and then the sigma of summation once again. So this is for our, this one is for the observed, frequency of the observed data, and then this one is the frequency of the expected data. It will be squared and it will be divided by the expected data. So we have plotted here. So x squared is equals to 121 minus 100 squared plus 288 minus 150 squared plus 91 minus 250 squared, all over 100 over 150 and over 250. So this will end up to a total of 232.494. So now let's state the result. If x is greater than 5.99, reject null hypothesis. Then our x is equals to 232.494. Then we are going to reject our null hypothesis because it is much more greater than 5.99. So that is for our chi-square test for goodness of fit. State a conclusion. The ages of the 2010 populations are different from those expected based on the 2000 population. So moving on, we are having the test of homogeneity. Here we have more than one samples, unlike test of independence. We want to test whether these samples are homogeneous as far as a particular attribute is concerned. So test of homogeneity. So same procedure. You're going to set up the null and alternative hypothesis. And we have to find the value using the formula, observed and expected frequency. Then we're going to find the degrees of freedom. So this one is going to be different because it's row minus 1 and column minus 1. Then we're going to obtain the table value, and then we're going to describe whether it is acceptable or it will be rejected. So this is our problem. From the adult populations of 4 large cities, so let's put A, B, C, D as our large cities. Random samples were selected and the number of married and unmarried men were recorded. So we have the list of data for our married men, which is 137, 164, 152, and 147. And then we have our single or unmarried men. We have 32, 57, 56, and 35. Is there a significant variation among the cities in the tendency of men to marry? Okay, so we have our null hypothesis here. The four cities are homogeneous, and our alternative is the four cities are heterogeneous. So this is our data. So we are going to add our sum from the column to the row. So 137 plus 32, it will be 169. 164 plus 57, it will be 221. 152 plus 56, it will be 208. 147 plus 35, it will be 182. And this will total to 600, and this will total to 180. This will total to 780, and this will total to 780. So this is our data. This is the observed, and this is the expected one. So 106.9, go back here. This is our total, the summation. It will be multiplied to the total of the summation of the row. The summation of the column will be total to the summation of the row. Will be multiplied to the summation of the row. Then it will be divided on the total number, which is 780. So if you're going to have that one, then you're going to have 130, 170, 180, 140, 39, 51, 48, 42. This is our new data. So in here, we are going to subtract or get the difference between the observed and the expected value. So 137 minus 130, we have 7. 164 minus 170, we have negative 6. 152 minus 160, we have 108, and so on. And this time, our the difference will be squared. So 7 squared, 49, negative 6 squared, 36, and so on. After being squared, it will be divided by the expected value, which is 130, 170, 160, 140 on their corresponding value, and they will be having this result: 0.38, 0.21, 0.40, 0.35, 1.26, 0.71, 1.33, 1.17, and this will total to 5.80. So step 3, we are going to solve. So this is our formula once again. The summation of the observed minus the summation of the expected. It will be squared divided by the summation of expected. So the expected one. So our value is 5.80. And then table value of critical value, we're going to get the degrees of freedom. So we have 2 rows, so 2 minus 1, and we have 4 column, which is 4 minus 1, and the answers will be multiplied, and 1 times 3 is equals to 3. Our level of significance is the default one, which is 0.05. Moving on, so this is our table, and it was plotted. So 3, 0.05, then we will be having 7.815 as our result. So describe whether to accept or to reject the null hypothesis. So we're going to compare the critical value with the table value. So here is our calculated value, which is 5.80, which is less than the a table value of 7.815. So our inference is there is homogeneity. It means that cities are identical. There are no significant variation among cities in the tendency of men to marry. Moving on, we have the last of our chi-square test. We have the chi-square test for independence. The chi-square test for independence evaluates the relationship between two variables. It is a non-parametric test that is performed on categorical, nominal, or ordinal data. So a chi-square test for independence. So this is our problem. 500 elementary school boys and girls are asked which is their favorite color, blue, green, or pink. Results are shown below. So boys have shown interest of 100 for blue, 150 for green, and 20 for pink. And then girls shows interest of 20 to blue, 30 to green, and 180 to pink. So again, you are going to get the summation of the rows and the column. So this is 120, then it will be 120. 150 to 30 is 180. 20, 180 is 200. Then this will total to 500, and this will also total to 500. And if you're going to add this will be 300, and this will be 200. So using the alpha 0.05, would you conclude that there is a relationship between gender and favorite color? So again, this is our process. Define null and alternative hypothesis, state alpha, calculate degrees of freedom, state decision rule, calculate test and statistics, state result, and state conclusion. So this is our first one, step one, define null and alternative hypothesis. For our null hypothesis, for the population of elementary school students, gender and favorite colors are not related. For our alternative, for the population of elementary school students, gender and favorite colors are related. So this is our alpha, which is 0.05. The default one. Now let's calculate the degrees of freedom. Again, it will be row minus 1 and column minus 1. So we have 2 rows, so 2 minus 1 equals 1, and we have 3 columns. So 3 minus 1 goes 2. Multiply, it will be 1 times 2 is equals to 2. Now, our degrees of freedom is 2, and our alpha is 0.05. So our table value will be 5.99147. So state our decision rule. If x squared is greater than 5.99, reject null hypothesis. And here we are going to calculate our data. So this is again our formula. So here it will be like this, boys blue. So 120 multiplied by 300. So this one will be this one divided by 500, and we're going to have 72. So that is how we get the data. And it will be so on, and it will be like this one. So calculate, we have 100 minus 72 squared divided by 72. So 20 minus 48 squared divided by 48. And so on, and we will be ending up into 276.389. Now let's state the result. If x squared, or the chi-square test for independence, is greater than 5.99, rejects null hypothesis. Then our data is 276.389. So that means it is rejected because our rule is to reject if it is greater than 599 and it is much more greater. We have 276 and 3.389. So it will be rejected. So state conclusion, and in the population, there is a relationship between gender and favorite color. Now let's have the Spearman's rank order correlation coefficient. What is the Spearman's rank order correlation coefficient? So this measures of the strength and direction of association that exists between two variables measured on at least an ordinal scale. So this is our formula. It will be a small p and then is equals to 1 minus 6 sigma of d, your value, squared, and n multiplied by n squared minus 1. So this is our ranking table. This is our table. And if you are going to do this, you have to rank your data so that you will not get confused whenever you are going to look at your data once again. So you have to rank it from 1 until its highest point. So we have a ranking here, but it was not arranged. So let's move and arrange our data. So our data consists of physics and math score. So let's start with this one. So let's assume that P is for physics. So P is for physics. And then the scores it has is 35, 23, 47, 17, 10, 43, 9, 6, 28. So that is for our physics. Now let's have for our math. This is for our math. M for math, we have 30. We have 33. We have 45. We have 23. We have 8. 49. 12. 4. And 31. So let's arrange it vertically with the rank. So we have 9 participants. So let's put our rank first, the same color as what they have started, a different one. So we have, this is for P, we have number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9. So the one that ranks highest is 47. 47. So this is gone. And we have the second one, which is the 43. 43. The third one will be 35. The fourth one would be 28. The fifth one would be 23. The sixth one would be 17. The seventh one would be 10. The eighth one would be 6. And the last is 4. Okay. Now let's have our math. For our math, the first one is 49. The second one is 45. The third one is 33. The fourth one is 31. The fifth one is 30. And the sixth one is 23. The seventh one is 12. The eighth one is 8. The ninth is 4. Okay, there you go. So we have our data. Now we are going to find our D. So D is equals to X minus Y. So it will be physics minus math. So we will be having this one. So physics minus math is equals to 47 minus 49, we have negative 2. 43 minus 45, we have negative 2. 35 minus 33, we have 2. 28 minus 31, we have negative 3. And then 23 minus 30 equals negative 7. 17 minus 23 is negative 6. 10 minus 12 equals negative 2. 6 minus 8 is equals to negative 2. 4 minus 4 is equal to 0. Then after that one, this is P minus M. So after that one, we are going to square our data. It will be squared. So negative 2 squared is 4. Negative 2 is 4. 4. Oh, this is 9. Negative 3 is squared 9. 49. 36. Oh, 36. 4. 4. And 0. And then we're going to get our summation. We are going to sum up the squared. So it's 4 plus 4 plus 4 plus 9 plus 49 plus 36 plus 4 plus 4 plus 0 is equals to 114. So we will be in total of 114. Now, so our formula is R S, because this is the same with Pearson. Pearson, and this is minus 1 minus this is 6 summation of d squared over n times n squared minus 1. So let's plot. So we have 1 minus 6 summation of d squared. So this is our d squared, which is times 114 over, this is 9, and this will be 9 squared minus 1. So 1 minus 114 times 6 is equals to 684. So 981. This will be 81. 9 squared is 81. Minus 1, it will be 80. So 1 minus 684, 9 times 80. It will be here. 1 minus 684 minus 720. So 1 minus 684 divided by 720, it will equal to 0.95. So 1 minus 0.95 is equals to 0.05. So this is your spearman. And this denotes that this belongs to the 0.00 to 0.20, and this denotes indifference and negligible relationship. So that will be for our spearman, and that will be for our review. So thank you very much, and I hope you learned, and I'll see you next time. Goodbye, everybody.